the end of our last lecture, we had introduced the topic of pressure. Pressure is the force exerted per unit area. It can be the force exerted per unit area by a block of metal that I place on the floor. It could be the force exerted per unit area by the water at the bottom, pushing on the bottom of the swimming pool. But more to the point of what we're going to use it for here, it will be the force exerted as particles of gas are flying around in a chamber and striking the walls. They exert a force on the walls, and if you average that force over the area of the wall, you will have the pressure that the gas exerts on the wall. Now, of course, the atmosphere surrounding our planet Earth also exerts a pressure, and the molecules in the atmosphere of the Earth are gravitationally attracted to the Earth, believe it or not, and they are held there by the pull of gravity. And as you get closer and closer to the surface of the Earth, the density or mass or number per volume ratio of air molecules, nitrogen and oxygen mainly, is greatest near the surface. And as you get to higher and higher altitudes, this density of the air lessens. So when you're nearest the surface of the Earth, the density of the air at the surface creates more strikes of air molecules as they are moving around due to the temperature present, and they're moving randomly, so they're striking you evenly all over your entire body, so that they're exerting the same pressure anywhere on you or any other object at the surface of the Earth. Now, as you go to higher altitudes, there's less of a density of air, so there's less striking on you over the same area of your body. So the pressure you experience as you increase in altitude will go down. And we see here a little chart, which of course, again, I don't expect that you would memorize this chart. Instead of listing it by the pressure in atmospheres, remember an atmosphere is how much air pushes on you at sea level. What this chart is showing you is the pressure that air is exerting relative to a column of liquid mercury. Again, we had talked about liquid mercury and its push, and how Torricelli used it to design a measurement of pressure. And what we remember, I hope, is that if you stack a column 76 centimeters or 760 millimeters high of mercury, it will be pulled by gravity down to the surface of the Earth with the same push on that surface that the air is pushing on the surface of the Earth. So 760 millimeters of mercury is 1 atmosphere of pressure. And you see at sea level, you have, as the third column lists, a pressure of 760 millimeters. By the time you get to Denver, which you see there is an altitude of 1.6 kilometers, and that is as advertised by their announcements, it's the mile-high city. 1.6 kilometers is a mile high. The air pressure in Denver is down to 630 from here in New Orleans being 760 millimeters of mercury. So that's a drop off of about almost a fourth, not quite, of the air pressure when you get to that altitude. Notice by the time you get up to the top of Mount Everest, the pressure at the top of Mount Everest is 270 millimeters of mercury due to the rarefaction of the air. And again, that is about 1/3 the pressure that we experience here at the surface of the Earth. Let's look at a tube full of mercury, a U-shaped tube full of mercury that we will call a mercury manometer, which is a handy device to measure the pressure exerted by a gas. Now let's look at the top left flask first of all. I have a sealed flask in which I have placed, of course, it's full of some gas, maybe it's just the air that I put in there, but it could be any other gaseous sample. Then I attach that sample of gas inside the flask through a hose to the left side of the manometer. Now I want you to notice that arm of the manometer at the top. It is closed, sealed. I have the sealed left arm of the manometer, then the blue at the bottom represents the mercury, and you will notice that it is filling the bottom of the tube to a height equal on both sides of that tube. Then notice that the right side of the manometer has an open end tube, and running down into that tube are air molecules, so air is pushing on the surface of the right column of mercury. As a matter of fact, the gas in the chamber is running up through the flask into the tube, down through the left side of the manometer and pushing on the left surface of the manometer. Now, just like you would experience on the playground, this manometer fluid is acting like a seesaw. The left manometer arm is being pushed upon by the gas molecules in the flask. The right manometer arm is being pushed by the air molecules coming down the open tube. And much like a seesaw, again, if the forces in action on opposite sides of the fulcrum, or the bottom of the puddle, are equal, then the seesaw is balanced. So because the level in both arms of the manometer is the same, that means that the air is pushing down just as hard as the gas in the chamber. Now let's go to the upper right manometer picture. Here again I have a flask full of gas pushing on the left sealed arm of the manometer, and I have an open end on the right, and air is pushing down on the right end of the manometer. Now I notice an imbalance in the levels of mercury in the two arms. Now the mercury column is static, and it is only when the mercury column is static, meaning it's not moving, that you can make this assertion that I'm going to make. If the mercury column is still moving one way or the other, you must wait till it stops moving before you can make the assessment of what the pressure of the gas is inside the chamber. And I'll clarify that maybe more in a second, but let's suppose for the instant here that the gas manometer or the mercury manometer arms are stationary. They're not moving any further. So once again, on the left side, the gas molecules are rushing up the hose and down the tube and pushing on the left side of the mercury. Air from the outside is running down through the open end of the right manometer arm, pushing down on the surface of that liquid, yet the liquid is in an imbalance. And what this is implying again is like a seesaw would do. If you have a heavy person on one end, that side of the seesaw goes down. So this is an indication that the gas in the chamber is pushing harder than air, and we can even quantify how much harder than air it is pushing, provided that the liquid is mercury. Well, actually, provided that it's anything, but we have a nice connection between atmospheric pressure and mercury manometer inch or millimeter pressure. So I measure the difference in height of the left arm and right arm of the manometer, and I get there's a 1,300 millimeter difference in height between the two arms. So of course this 1,300 millimeters of mercury is being pulled by gravity downwards and exerting a force on the right tube. So air is also running down into that tube and exerting a force in addition to the force that the mercury in the tube is supplying. So the total added force in the right tube compared to the left tube is the sum of the air and the height. That's the difference in push from comparing what the gas is doing to what the air is with the help of mercury. So the air in the chamber, the P gas, is equal to the air pushing down on the right column plus the mercury pushing down on the right column. That is 760 plus 1,300. That's a total of 2,600 millimeter of mercury pressure that the gas in the chamber is exerting. Now, if I would like, I could convert that back to atmospheres of pressure by using the conversion factor that 1 atmosphere is 760 millimeters. I line it up to cancel my millimeter units, and it gives me 1,600, times 1 divided by 760, or 3.4 atmospheres is the pressure being exerted by the gas in the chamber. Now let's look at the bottom picture on the bottom left. Here I notice that the imbalance in the arms of the manometer is again not in the direction as we saw above, but it is opposite. The air is pushing down harder on the right arm than the gas is pushing as it makes its way into the tube on the left arm. And as a matter of fact, the gas needs some assistance from the gravitational pull on Mercury in order to match how hard air is pushing on the right. So I measure the difference in height between the two arms of the manometer, and I find them to be 400 millimeters difference in height. That means there's a 400 millimeter mercury difference between the gas pressure in the chamber and the air pressure, which is pushing harder on the outside. So the pressure of the gas is the air minus this height h, and that is 360 millimeters of mercury total. Now I can, again, divide that by 760 and convert that into a little less than a half an atmosphere of pressure is being exerted by the gas in the chamber. Now again, one more thing about those arms, if they're static or moving. They must be static before you can draw these conclusions. If they are still in motion, what that's saying is you haven't reached the point where there's enough mercury in the pile to be pushing down hard enough to match the pressure caused by the gas pushing on those tubes. So again, as long as the thing is moving, you have to wait till it stops. It doesn't matter if it's moving up on the left or up on the right. You have to wait until it stops in motion. Then you will know how much total mercury assistance, if you like, the density of the mercury being pulled by gravity has to be aided and used to aid what the air is pushing or what the flask gas is pushing in order to match the other side to make a comparison. Now let's turn our attention to the measurement of temperature. Now we've done a little bit of discussion about temperature when we did our thermodynamics, and what we can ultimately think of as a simple meaning for what temperature is. It's a description of the ambient energy bath that a material or an object or you or I are subjected to based on the ambient conditions around us. Of course, for instance, a building or a room that you're in with a furnace in the basement or in the attic or wherever is pumping heat energy into the room, so you're constantly being bathed by heat energy. The thermometer arm level will move up and down dependent on what level of motion the molecules have in the air of that room. And the greater the motion of the molecules, of course, that goes up with temperature, as we talked about in the kinetic theory. So the molecules in a hotter room will slam into the glass containing an expanding liquid with greater velocity in a hotter room, and that will transfer momentum into the liquid in the tube, and the liquid will expand according to how much energy is transferred into it due to the motion of the molecules slamming into the glass. And based on the expansion of the liquid, it was used to design a measurement scale to relate the temperature to the energy content of the surroundings to that device. And of course, the device we're talking about is known as a thermometer. Now, not only can you do this with expanding liquids, it became a little more accurate to do it by conduction of a conductor and looking at how much current will flow through the conductor, so we can have an electronic thermometer, and that's more commonly used nowadays, an electronic thermometer, because when you put current carrying wires in an energy bath, their resistance increases, so the current of electricity flowing through them decreases as you put more energy into the circuit. So we can again use that to devise a scale to figure out what the temperature or energy bath of the room is based on how much current is flowing through a conductor. Now, the original mercury thermometer was devised by Fahrenheit himself, and he also came up with a temperature scale. We'll look a little bit more at the temperature scale on the next slide. It turns out that for laboratory calibration purposes, this scale was not deemed as easy to set scales of, to set up a temperature scale with. So Celsius, the person you see on the right, came up with the so-called Celsius temperature scale very shortly thereafter that Fahrenheit had come up with his scale, and so it became the standard that was used. Oftentimes Celsius is also known as centigrade, but we're going to call it Celsius here, and it's the more typical temperature scale that we will use, even though in America the Fahrenheit temperature scale is much more popular, as you well know. Just some comparisons between temperatures on the Fahrenheit and Celsius scales. We note that the starting point, if you like, not really the starting point, but the reference point for the two scales is 0 on the Celsius and 32 on the Fahrenheit scale. Those are the freezing points of pure water. Now, in actuality, those freezing points should be measured at sea level atmospheric pressure. So at atmospheric pressure, pushing down on the surface of liquid water at 0 degrees Celsius, there's enough energy around it so that the molecules will coalesce together and change from the liquid to the solid phase, or at 32 degrees Fahrenheit. That is the case. Now, body temperature is roughly 98.6 or 37 degrees Celsius. The boiling point of pure water is, again, when 1 atmosphere of pressure, or 760 millimeters, is pushing on the surface of the liquid. It will change phase spontaneously to a gas, provided there's enough energy in the surroundings so that the temperature measurement on the Celsius scale would be 100 degrees, and the temperature measurement on the Fahrenheit scale would be 212. Now, as a matter of fact, that's why the Celsius scale was set to be able to be calibrated in labs so much easier. You just get some water and freeze it, and at atmospheric pressure, mark off a mercury column, call that 0, then get the water and boil it against atmospheric pressure. The liquid in the thermometers expands, and when the water is boiling, you mark it off again, set that at 100, then divide it up into 100 graduations, or make it centigrade. Now, notice that there is actually, believe it or not, a coincidence point between the Celsius and Fahrenheit scales. Those would be at the value of -40 degrees on both scales. Now, do I expect you to know these numbers? Of course not. As a matter of fact, this is not that relevant, but it's just some points of interest for our temperature scales. When Gay-Lussac was experimenting with gases, he was able to look at what volume they would occupy as he changed the temperature. Basically, what he could do is fill up something like a balloon and heat or cool the balloon, and look at the expansion or contraction that the balloon would undergo as he heated or cooled the gas. So what he did was, of course, was work with temperatures he had available to him, and at the time in the late 1700s that he was probably doing these things, or the early 1800s when he was doing these things, there wasn't a wide range of temperatures available like there may be today. So he could only do a limited study of how the temperature and volume were related. Well, one interesting thing was, over the range that he could do the experiments, he found that he could make the plot of the volume of the gas versus temperature linear if he chose his temperatures exerted in a certain way. If he chose a certain temperature scale, there was a linear relationship between volume and temperature, meaning if you double the temperature, you double the volume, triple the temperature, you triple the volume, and so forth. Well, there was a limit to the temperatures he could work with, but what he did was something very clever. He took his nice linear line or expression and extrapolated it, meaning the dash is representing beyond the temperatures he could work with, he could still just extend his line, which means extrapolate the data, so that he could take the temperature down to other values other than what he could experiment with. And what he came to the conclusion was, if it were possible for him to come to what we now know to be negative 273 degrees C, that the gas would occupy zero volume, or that the gas would vanish entirely if he could take it down to this magic temperature. Now, it turns out that Gay-Lussac didn't quite understand the nature of gases, and they weren't quite worked out completely yet. They didn't quite understand that the gas would condense before it would vanish. Okay, so as the molecules slow and slow and slow and get closer and closer together, they also have intermolecular force that makes them stickier to one another. And now we understand that the gas would change phase to liquid and not just continue its gaseous volume all the way down until it disappeared. But still there was this intriguing value of what we now would know to be negative 273.15 degrees C, where this gas should reach zero volume by extrapolation of the linear line. What was soon pointed out by William Thomson, who later became known as Lord Kelvin, what he pointed out was that this magic value that Gay-Lussac had found, where it appeared the volume of the gas would vanish if you could possibly get to that temperature, what Kelvin surmised was this was the bottom of the temperature scale, because what has happened if you reach that magic temperature of negative 273.15 degrees C, you have removed all energy from the ambient surroundings. There's no more energy in the air around you. It won't be air anymore. It'll be solidified. As a matter of fact, everything would be a solid when you reach this temperature, because the motion of all matter ceases at absolute zero. On the Celsius scale, that's minus 273.15. On the Fahrenheit scale, it's minus 459.67 degrees F. So this led Kelvin to devise his own temperature scale, which was based on Celsius, and it starts at the bottom of the bottom. It starts at zero, where for the weirdness of Celsius or Fahrenheit being relative scales, where they set them based on pure water freezing, they set zero where pure water freezes, but there are possible temperatures well below the freezing point of water, and so you have nothing possible but to make negative temperatures on both the Celsius or Fahrenheit scales when you get below temperatures below the point at which water will freeze. So what Kelvin did was design a scale which truly does measure energetics, because there is no such thing as negative energy. When you're at zero ambient energy surrounding you, you are at 0 Kelvin. As soon as you put any amount of temperature in, you have some energetics in the room, and that's a positive amount of energy in the surroundings. So this would be an absolute scale in the sense that all numbers on this scale are positive. They start at 0 and go upward, unlike, again, the Fahrenheit or Celsius scale, where negative temperatures are certainly possible. On the Kelvin scale, all temperatures are positive, and this is the scale that is decided upon that should be used for the System International. Anytime we report temperature, we should report temperatures on this absolute temperature scale. And again, To get the absolute temperature, you simply will take the Celsius temperature and add this magic number 273.15. Notice if you could get all the way down to the coldest possible Celsius temperature, that would be by putting that number in for degree C in the equation, it would be at 0 Kelvin. And room temperature, roughly 25 degrees C, is 298 Kelvin. The boiling point of water, 100 degrees C, would be 373 on the Kelvin scale. Now, every time we do calculations involving gases, please remember to change your temperatures onto the Kelvin scale, and you should certainly be familiar with the formula K equals degrees C plus 273.15. Now then, if you take a gas sample and you measure parameters which define its physical state of its pressure or force over area, its volume, its temperature, and the amount of the gas in the sample, it turns out that these four variables have an interrelationship so that there's a proportionality between them. And as a matter of fact, P times V is proportional to N times T, where P and V are the pressure and volume, N and T are the moles and temperature. So for any gas behaving under the kinetic theory, again, remember, you can review the rules that we set out for gases obeying kinetic theory. If you multiply the pressure times the volume, it'll be proportional to the moles times the temperature. So if you double the pressure times the volume, you will double the mole times the temperature. If you cut the pressure times the volume by 1/3, you will cut the moles times the volume by 1/3. Now these things are proportional to one another. That does not mean they're exactly equal. You need to set into the equation a so-called proportionality constant to make the two sides of the equation equal. So again, P times V is proportional to N times T. To make P times V equal to N times T, you got to put a fudge factor in the equation. And that fudge factor has been universally given the symbol or the designation R. So to set the equation of these behaviors equal, PV equals nRT. This is known as the ideal gas formula. And what is an ideal gas? An ideal gas is a gas which is obeying kinetic theory. Kinetic theory means it has no mechanism of attraction between the gas particles. They're not gravitationally or electrostatically pulled towards one another. All of their energy is energy of motion, or all of their energy is kinetic energy. And as the temperature goes up, the amount of this motion goes up, so that the pressure they occupy or push with and volume they will occupy will go up proportional to how many molecules are present and how fast they are moving around in the chamber. So it ends up then that PV equals N times R times T. This is the ideal gas formula, again, for any gas obeying kinetic theory. Now, what is this proportionality constant R? Well, notice if I rearrange the equation, R is equal to PV divided by NT. And it turns out that R has a value of 0.0821 liter atmosphere over K mole. Now, let's note those units. They come directly from measuring pressure in atmospheres, measuring volume in liters, measuring the amount of gas in moles, measuring the temperature of the gas in Kelvin. So, anytime you use the ideal gas formula, you must use pressure in atmospheres, volume in liters, temperature in Kelvin, and the amount of gas present in moles in order to use this proportionality constant R of 0.0821. If you do not have these values in those particular units, they must be transformed to these units in order to use this formula correctly. Now remember again, this formula holds for any gas behaving ideally or any gas following kinetic theory. It works very well even if we approximate any real gas that we have under assuming this type of behavior. And as well, keep in mind that you must have the values in the units prescribed of liters of volume, pressure in atmospheres, temperature in Kelvin, and amount of gas in moles. When can we expect gases to behave ideally? Well, again, they have to be following kinetic theory, and in the instance of following kinetic theory, that essentially means they have no intermolecular force, they don't have any attractions towards each other. So when can they have no attractions toward one another? When they're far apart, or when they're in large volume. Now, being in large volume is naturally implying that there's not many of them. It's either just a huge container, or there's not many of them in the container. Well, if there's not many of them in the container, they're not going to be striking the walls very often, so they will be at low pressure. So either if they're occupying large volume or at low pressure, we can believe they'll be behaving ideally. Again, the pressure is some indication about the size of the volume of the container, as we'll see, but it's also saying something about how many of the molecules are present in the sample. Now, also one other possibility is that if they are at very high temperature, because remember, the amount of motion they possess is tied directly to their temperature. The hotter the temperature, the more quickly they're moving. The more quickly they're moving, the less likely they are to stick to one another. So the less likely they are to stick to one another, the lower their intermolecular force, and the more ideal they begin to behave. Let's look at an example of using the ideal gas formula. Let's answer the question, what volume does 1 mole of gas occupy at 0 degrees C and 1 atmosphere pressure? First of all, we should note that this is known by chemists as standard temperature and pressure, STP. STP is the condition of 0 degrees C, or the freezing point of pure water, and 1 atmosphere pressure, the pressure exerted by air at sea level. So what I will do is solve for V. V is nRT over P, and I just stick my numbers in, 1 mole, R with its units, and now notice I have converted the temperature from Celsius into Kelvin, so I'm putting in 273 Kelvin, and I'm going to divide by the pressure in atmospheres of 1. Notice all units in R cancel except V unit of liters. Notice the Kelvin units cancel, atmosphere units cancel, mole units cancel. My answer comes out in volume units as it should. So dimensionally, I'm doing the correct thing. So when I put the numbers together, I find the volume of 1 mole of gas at STP is 22.4 liters. Now, any gas behaving ideally at STP would occupy 22.4 liters. Now remember, a 2-liter Coke bottle, we all know what that looks like. This is a little over 11 2-liter Coke bottles that an Avogadro's number of gas particles should occupy. This is the volume air occupies if it's behaving ideally. CO2, O2, methane, anything I choose in the gaseous phase should all occupy 22.4 liters at standard temperature and pressure. We can use the concept of the volume that gases occupy at STP. We know 1 mole of gas occupies this volume, and the molar mass of various gases to interpret what the density of any gas behaving ideally would be at standard temperature and pressure. We can easily find that by finding the molar mass of that gas and dividing it by the molar volume of that gas. Now, the molar volume at STP means what volume would 1 mole of gas occupy at 0 degrees C and 1 atmosphere pressure. Well, we've determined that to be 22.4 liter per mole. No matter what the gas is, as long as it's an ideal gas, that's what it would occupy. And then from the molar mass of, say, methane, by adding up 4 H's and a C, I get 16.04 gram per mole. I divide that by 22.4 liter per mole, and I find the density of methane to be 0.716 gram per liter. So if I evacuate a liter water bottle and only pump in 1 mole of methane gas, it'll weigh 0.716 grams more than it weighed evacuated. Now I could also convert that to grams per milliliter by noting there's 1,000 milliliters per liter, so the density of methane is 0.000716 gram per milliliter. Do the same thing for carbon dioxide, which has a molar mass of 44.01 gram per mole. If it's being ideal, that it would occupy a volume of 22.4 liter per mole. So when I divide those numbers together, I find the density of carbon dioxide to be over double that of methane, 1.96 gram per liter, or 0.00196 gram per milliliter. Look at the example of how many grams of methane gas would occupy 2 liters at STP. Well, my equation PV equals nRT is solved for the number of moles of gas. Now, of course, STP is 1 atmosphere pressure and 273 Kelvin, or 0 degrees C. So when I stick in my values, I find that the number of moles of gas when it's occupying 2 liters of volume is 0.0892 moles. Then I can just use the molar mass of methane to find that that would be 1.43 grams of methane. This fourth example, we take 1.59 grams of helium, and it's occupying 325 milliliters of volume. It's at a pressure of 915 millimeters of mercury. We want to know what Celsius temperature this gas must possess. So in order to work any of these ideal gas problems, you need to know 3 of the parameters, and the 4th can be determined based on the ideal gas formula. But since R has volumes of liter, atmosphere, K, and mole, that means that the moles, the material amount has to be in moles of stuff, the volume has to be in liters of space, and the pressure has to be in atmospheres of measurement. So I take my mass in grams, use the molar mass and find the moles of HE, take my volume in milliliters, convert it to liters of volume, take my pressure in millimeters of mercury, and convert it to atmospheres of pressure. Remember, you cannot use R in the units that is prescribed for it unless these values are in the particular form that you see on this slide. Continuing the problem, example 4 that we started on the previous slide. I now have my pressure in atmospheres, my volume in liters, and my amount in moles. So I can now solve for T by putting PV divided by NR. Notice all units cancel except the temperature unit. And when I'm done, I calculate 11.9 Kelvin. But as the word statement above says, it asks for the Celsius temperature of the gas. So using the Kelvin formula, K equal degrees C plus 273.15, I determine that the temperature in Celsius is negative 261.2 degrees C for this gas under those conditions. So far we've been describing physical change of the gas, meaning just heating it and cooling it and squeezing it and changing the volume and all these other sorts of things like that, but really not changing the composition of the material. Now let's look at a chemical reaction here that is very common when you put acids together with metals. You get the evolution of hydrogen gas. As a matter of fact, this is how you would clean your pool deck. The cement on the outer layer that gets oxidized and filthy, you dump a little material on there, the pool cleaner, which contains acid, and it bubbles a layer of the cement away, making H2 gas, and then you have a nice clean layer of unoxidized cement underneath it. It looks really nice and pretty. So here I'm doing the same thing with metal. This is called etching a metal, really. You mix it with some acid, and it makes, as you can see, this is kind of like a single replacement reaction where the Mg is kicking the H out of this HCl compound and making MgCl, and then evolving H2 gas. Now the stoichiometry, or balancing coefficients of this show that 1 mole of Mg reacts with 2 moles of HCl to make 1 mole of MgCl2 and 2 moles of H2. And you notice the arrow pointing upward means I got H2 gas evolving, if we like to say, or bubbling out of the aqueous solution that I dropped the magnesium into. There'll be bubbles of H2 evolving. So the question I'm going to pose is how many milliliters of H2 gas would be generated if I completely react 1 gram of Mg at STP. So now this becomes a limiting reagent problem where 1 gram of Mg is my limiting reagent. So I need to find how many moles of H2 can be generated by complete reaction of 1 gram of Mg. Now this is a topic we took up earlier in this lecture set. I take my 1 gram of Mg and dividing it by the molar, dividing the molar mass of Mg into that gram, I find 0.0411 mole of Mg. Then from the stoichiometry of the balanced equation, 1 mole of H2 is formed for every 1 mole of Mg reacting. I know that I will have 0.0411 moles of H2 evolving from 0.0411 mole of Mg reacting completely. Now what I can do with that number is stick it into my magic ideal gas formula to solve for the volume. The volume is nRT over P, and I put the STP values of pressure and temperature into the expression, and I get that the volume of the gas at STP is 0.921 liters, or 921 milliliters of volume. Let's look at a second example of gas stoichiometry. Here I'm reacting elemental aluminum with nitric acid to make aluminum nitrate and H2. So we pose the question of asking how much aluminum would be required to make 125 milliliters of H2 at the conditions of 20 degrees C and 475 millimeters of mercury pressure. Well, I want to make 125 milliliters of this. Again, ultimately, I'm going to be using the ideal gas formula to find the moles of H2 that I have at these conditions. So I have to have my volume of the gas I'm making in liters. So I have 125 milliliters is 0.125 liters. I have the pressure of 475 millimeters mercury, has to be in atmospheres. So I divide by 760 to find that it's 0.625 atmospheres, and the temperature of 20 degrees C must be in Kelvin. So I add 273 and find I'm at 293 Kelvin. Using the pressure, volume, and temperature on the previous slide, I will find the moles of H2 gas that are going to evolve under those conditions. And I get 0.00325. Notice all units canceling as they should, and I'm only left in mole units. Now what I'm going to do is use the balanced chemical equation at the top to convert the number of moles of H2 produced into the moles of aluminum that must react in order to pull that off. There's a 2 to 3 ratio of reacting ALs to producing H2s. So I find 0.00217 mole of aluminum must react if I want to form 0.00325 mole of H2. To find how much aluminum I must weigh out, I use the molar mass of aluminum and find that I must weigh out 0.0584 grams of aluminum if I wish to produce 125 milliliters of H2 at the pressure and temperature of the experiment. Now we introduce Dalton's law of partial pressures. This is the same Dalton who is celebrated for the idea of atomic theory. We talked about him earlier at great length with regard to that. He was also a so-called pneumatic chemist studying the properties of gases like many of his contemporaries. And one of his ideas he came up with was the idea of partial pressure that a gas would occupy. Consider the chamber on the right, and it has some red spheres representing gas A and some blue spheres representing gas B. And each of these will exert a partial pressure PA for the red spheres, partial pressure PB for the blue spheres, and the total pressure in the chamber, I'm going to claim, is simply a sum of these individual pressures exerted by these gases separately. So think of it like this. Suddenly, the red spheres all disappear and only the blue spheres are in the chamber. There's a certain number of moles of them at a temperature, pressure, or temperature and volume. So they will strike into the walls of it, exerting a pressure that we will call PB. Now let's magically make the blue spheres disappear and the red spheres appear. They're in the same volume at the same temperature. Now there might be a different number of moles of them, but they will run around in there striking the walls to exert a pressure that I will call PA. Now the PA molecules don't feel each other, so they have no attraction to one another because they're going to behave ideally. The PB molecules, if they're in there alone, have no attraction to one another. So when they're running around in there, they're behaving ideally, and they only have kinetic energy of their motion. So now when I'm mixing A with B, there's no interaction between the addition of the extra molecules in the chamber compared to what interaction there was prior to the introduction of the second gas. So both of these gases mixed together are still behaving ideally. They don't have any interaction with one another, so they won't affect the pressure of one another. So whatever pressure they would have exerted individually in the chamber, they will just now compound to exert as a sum of their individuals to give some higher total pressure when you mix them together. So for mixtures of gases in a container, each will exert its own partial pressure, which would have been the same that it would exert it if it was in there by itself. And the more gases you add, you just add more partial pressures together to get the total pressure of all gases in the chamber. Let's look at an example of Dalton's law of partial pressure. Let's look at how it applies to air. Air is essentially oxygen and nitrogen. And if the partial pressure of nitrogen in air is 0.78, what would be the partial pressure of oxygen in air at sea level? Well, we would calculate the total pressure as being the sum of the partial pressures of the two gases present. And so PO2 would be atmospheric pressure minus the partial pressure of N2. And we would find then the partial pressure of O2 to be 0.22 atmospheres, which is roughly what it is at sea level. Let's look at the relationship between partial pressures and a new quantity we will call the mole fraction. So let's say we have gases A, B, and C occupying a container that has a volume V and temperature T. So all these gases are subjected to the same temperature. All these gases are in the same volume. I can calculate the partial pressure of each of them by solving the ideal gas formula for the behavior of each of them. And the only variable that differs for each gas is the number of moles of each gas. So PA is Na RT over V, PB is NB RT over V, PC is NC RT over V. Now the RT and V are the same in PA, PB, and PC. The only thing that differentiates them is the number of moles of each. Now, if these gases are behaving ideally, Dalton's law of partial pressures holds, so P tot is PA plus PB plus PC. And if I were to divide PA by P tot, I would get Na over RT over V divided by Na RT over V plus NB RT over V plus NC RT over V. So I'm just going to put the ideal gas formula equivalent of PA on the top and P tote on the bottom. And notice the RT and V's cancel in all places. So I come to the conclusion that PA over P tote equals NA over N tote. So I'm going to use this to define a new quantity that we will do on the next slide. What we're going to do is define the ratio of the moles of each substance to the total moles present in a sample as being known as the mole fraction. The mole fraction of A is the number of moles of A divided by the total number of moles, or AB plus C. The mole fraction of B is the number of moles of B divided by the total moles. The mole fraction of C is the number of moles of C divided by the total moles. Now, if there were 4 components present, I would have A, B, C, and D. Then I can have NA as being, or XA, excuse me, is NA over NA plus NB plus NC plus ND. So I would just put whatever number of components present as being the number of moles of each individual divided by the total moles. Now, when you have a mixture of components, the sum of mole fractions is always 1. XA plus XB plus XC must be equal to 1. And we can see that directly by just substituting what XA, XB, and XC are into the formula. I would get 1 when I put the sum of all components mole fractions together. Now for my definition on the previous slide, PA over P tote is equal to XA, or PA equals XA P tote, PB equals XB P tote, PC equals XC P tote. The relationship between the partial pressure of any gas and the total pressure of all gases in the chamber is that if you multiply the mole fraction of any gas times the total pressure, you will get the partial pressure of that gas. Let's look at an example of calculating partial pressures from mole fractions. I mix 15 grams of O2 with 15 grams of methane, and they exert a total pressure of 825 millimeters of mercury in some flask. So what is the partial pressure of each? I first divide the mass of each by the molar mass of each to find the number of moles of each. Then I find the mole fraction of each by taking the moles of each divided by the total moles, and I get the mole fraction of methane to be 0.666, the mole fraction of O2 to be 0.333. When I sum them together, I would get 1 for the total mole fraction of all the gas in the sample, as I should. Continuing the example from the previous slide, to find the mole fraction, I know the mole fraction of O2, so to find the partial pressure of O2, I simply must take this mole fraction times the total pressure of 825 millimeters of mercury. So I'm going to take 0.333 times 825. The partial pressure of O2 is 275. I will take 0.666 times the 825, or total pressure, and I get 550 millimeters of mercury as the partial pressure of methane. And of course, if I sum these partial pressures, I should get the total pressure back. Let's look at another example relating mole fraction and partial pressures. How many grams of N2 gas must be mixed with 20 grams of Cl2 gas so that the partial pressure of N2 is 0.7 atmospheres out of the total pressure of 1.1 atmosphere? Okay, so I can find the mole fraction of N2 because I know the partial pressure of N2 and I know the total pressure of the N2Cl2 mixture. So when I divide the P total into the PN2, I find that the mole fraction of N2 must be 0.636 in order to make the mole fraction, or the partial pressure of N2, to be 0.700. Now, what I can then do is use this to solve what the mass of N2 must be to make that mole fraction. So first, I know that I had 20 grams of Cl2 in there. And by dividing by the molar mass of CO2, I find I had 0.282 moles of Cl2. So I now know also that the mole fraction being 0.636 is equal to N2 divided, or the moles of N2 divided by the total moles, or the moles of N2 divided by the moles of N2 plus 0.282. So I have a little equation that I must solve for the moles of N2. How do I do this? I distribute and multiply both sides by moles of N2 plus 0.282, and I get the equation you see at the bottom. Moles of N2 equals 0.636 times moles of N2 plus 0.282. Now I'm going to distribute the 0.636 through the quantity in parentheses. So the first equation on this slide just repeats the last equation from the previous slide. The moles of N2 is equal to 0.636 times the quantity to distribute through moles of N2 plus 0.282. So I multiply both terms by 0.636, gather up the N2s on the left side of the equation. That means I'm taking one N2 minus 0.636 N2, and I end up with 0.364 N2 when I put all them on the left. That has to equal 0.179. So now I'm going to divide both sides by 0.364, and I get the moles of N2 must be 0.492. Now if I take that 0.492 moles of N2 times the molar mass of N2, I would find that I need to mix 13.8 grams of N2 with the 20 grams of Cl2 in order to get the partial pressure of N2 in the flask to equal 0.7 atmospheres. Now look at some other gas relationships. In particular, this time, let's look at how the pressure and volume vary for a fixed amount of gas that is held at a constant temperature. So we often call this an isothermal process on a closed system. Closed system means no matter is allowed in or out. Isothermal means the temperature is not allowed to change. So if I increase the pressure on a gas, it'll squeeze it to a smaller volume. That's what we're saying. Or in order to get the gas to occupy a larger volume, I need to push on it from the outside with less external pressure. So these relationships are exactly inversely proportional. This was described by Robert Boyle way back in the 1600s, and it's known as Boyle's law. Pressure and volume are inversely proportional for a fixed amount of gas at constant temperature, and that means exactly inversely proportional. Doubling the pressure will cut the volume by 1/2. Cutting the pressure by 1/3 will triple the volume. Now in numeric form, Boyle's law states that P1 V1 equals P2 V2. Let's look at what kinetic theory would have to say about Boyle's law. Let's suppose I have a gas sample that is in a balloon, a flexible chamber that I can change the volume of at will. Now let's make sure we maintain the temperature fixed for this sample of gas, and it's closed, meaning I'm not going to let any of the gas particles in or out. Okay, so what happens then if I squeeze the same sample of gas into a smaller chamber? Well, as the volume goes down, the molecules are closer and more often around the walls of the chamber. They hit the wall more often, so that will lead to an increase of pressure on the inside of the chamber. So as the volume goes down, the pressure goes up. Conversely, if I take the same size sample of gas, the same temperature, now expand the chamber without making any other changes. Now the molecules have a further distance to go before they can encounter the wall. They encounter the walls less often, so naturally the pressure inside the chamber will go down. Let's look at how we could derive Boyle's law from the ideal gas law. Let's consider two experiments in which I allow the pressure and volume to vary while the amount of gas and temperature are held fixed. So I'm going to measure an initial pressure and an initial volume that I'll call P1 and V1, and at those conditions I will know how much gas I have present. I'm just going to call that N, and I know what temperature the system is at. I will call that T, so that P1 V1 equals nRT1. Now let's design a second experiment where I allow the pressure to change from that value to another value. When that happens, the volume will change as long as the temperature and the amount of gas are held fixed. So I have a new P2, a new V2, but the temperature and amount of gas are the same from experiment 1. So P2, V2 equals nRT. But now nRT and nRT, the right-hand sides of these two equations, are the same. So the left-hand sides of these two equations must be equal as well. So therefore, P1 V1 equals P2 V2. Let's look at a first application of Boyle's law. Suppose we have a gas occupying 20 liters at pressure 1 atmosphere. What volume will the gas occupy if I up the pressure somehow to 4 atmospheres without letting any gas out and keeping the temperature fixed? Okay, now let me first point out, when I have changing conditions, I wish to use a formula such as Boyle's law compared to when I have conditions that are not changing. I will use the ideal gas law. So in this case, P1 V1 equals P2 V2. So P1 is 1 atmosphere, V1 is 20 liters. Those are my initial conditions. I change the pressure to 4 atmospheres. What will happen to the volume when I do so? I solve the equation for V2, and I get that it's P1 V1 over P2. Putting in the numbers, I find the volume will be 5 liters when I up the pressure to 4 atmospheres. Now notice, I have 4 times the pressure. I have 1/4 the volume being occupied by the gas. Let's look at a second Boyle's law example. Suppose I have a gas occupying 14.2 liters, pressure 480 millimeters of mercury. What pressure will this change to if the gas is occupying 30.8 liters? Now I have the same temperature and the same amount of gas. So again, I know my P1 and V1 to be 480 millimeters of mercury and 14.2 liters. I know my V2 is changing to 30.8 liters. If the temperature and amount are held fixed, I can use my Boyle's law to solve for P2. Notice the volume units cancel. My answer will come out in millimeters of mercury. So in this case, I didn't have to convert to atmospheres. I could, and it wouldn't change the correctness of the answer. But when I use the units that I'm showing here, I will get that the volume, when the volume changes from 14.2 to 30.8 liters, the pressure goes down from 480 millimeters to 221 milliliters. The volume went up, so the pressure must coincidingly go down. Let's now move to what is known as Charles's law. Charles's law is the temperature-volume relationship. And we will first note that we're going to, again, have varying conditions where we're going to be changing the temperature and see how that will affect the volume the gas will occupy. So we have a fixed amount of gas in a closed system at constant pressure this time. The temperature and volume, it turns out, are directly proportional. Now, in order for there to be direct proportionality, the temperature must be measured in Kelvin. And what we're saying is when the temperature goes up, the volume goes up. And as a matter of fact, they go up proportionally. So if you triple the Kelvin temperature, you will triple the volume the gas occupies. And when the temperature goes down, the volume goes down. Cutting the Kelvin temperature by a quarter cuts the volume by a quarter. Now, then the relationship mathematically that will show this is V1 over T1 equals V2 over T2. This was discussed in the 1700s by Jacques Charles. See if we can use kinetic theory to describe what's going on with Charles's law. Let's consider a balloon with flexible walls that is filled with a fixed amount of gas that can't get in or out, and we will now let the balloon come to the volume it will occupy, and when it comes to its shape and size that it will end up at, the walls of the balloon are not moving because the internal push of the molecules inside the balloon is exactly the same as the external push of the air surrounding the balloon on the outer walls. So the inner walls are being pushed to the same extent the outer walls are pushed. The walls aren't moving. The pressure on the inside of the balloon is the same as on the outside of the balloon. So now let me cool the balloon off as I do on the top right picture. When I cool the balloon off, what happens is the molecules in the balloon move more slowly according to kinetic theory. If they move more slowly, they hit the walls less often. They hit the walls with less force. So these lower the internal pressure because now they're moving slower and not hitting the wall as much. So now the air didn't change on the outside, so it's hitting the walls the same as it was before, so the external pressure is greater than the internal and the walls begin to move in. Now they will eventually stop when the walls get close enough so that it doesn't matter that the molecules are moving at such a lower temperature. Since the walls are closer, the molecules on the inside are just naturally going to hit the walls more often, and that will give them the pressure they need to balance the outside pressure and stop the walls from collapsing. So the balloon's volume will shrink. The pressure on the inside is the same as it was originally, and that's only because the temperature is down. Now let me take the balloon at the left at some initial temperature and raise that temperature as I do on the bottom right. The walls immediately begin to move outward because now the molecules on the inside are hotter, they're moving with more energy, they're hitting the walls with more force, they're creating more pressure on the inside, they push the walls outward because the air on the outside is pushing the same as it was before. But what happens is that the walls stop moving when they get far enough away that even though the molecules are moving greater on the inside, the walls are so much further away that the pressure on the inside again matches the pressure on the outside, but the volume has gone up while that has occurred. As we did with Boyle's law, we should be able to derive Charles's law from the ideal gas formula, PV equals nRT. Let's design two experiments as we did before. In the initial experiment, I'll measure the volume and temperature of the gas, V1 and T1. And I will measure them at some fixed amount of gas, N, and some fixed pressure, P. So if I solve the ideal gas formula, I know V1 over T1 equals NR over P. Now let's change the gas to new temperature so that the volume will change to a new volume, but I keep the amount of gas and the pressure fixed. So I have in the second ideal gas formula V2 over T2 equals NR over P. But the NR over P on the right of the two equations is the same. So the left-hand sides of the two equations must also be the same, or that V1 over T1 equals V2 over T2. Let's look at a Charles's law example. I have a gas occupying 18 liters of volume at 21.1 degrees C. What volume will the same gas occupy if I change the temperature to 78.45 degrees C? Again, I'm going to hold my pressure constant, so the formula V1 over T1 equals V2 over T2 holds. I rearrange and solve for V2 by putting in my T1 values and T2 values in Kelvin, not in Celsius. And notice I have cancellation of the Kelvin units, and I get that V2 is 21.5 liters. Let's stick some numbers in a Charles' Law example. I have a gas of volume 315 milliliters at temperature 16 degrees C. At what temperature will the gas occupy 89.5 milliliters if the pressure is constant? So V1 over T1 equals V2 over T2, which I'm going to rearrange to read V1 T2 equals V2 T1. I identify my initial temperature, but I convert it to Kelvin. Remember, formula must use Kelvin temperature. I have my initial volume that corresponds to the initial temperature of 16 degrees. I have my final volume V2, and I rearrange and solve the equation for T2, put my numbers in, and get that the final temperature after the volume has changed is down to 82.1 Kelvin. Continuing the problem from the previous slide, I found that the final temperature after I changed the volume was 82.1 Kelvin. The question actually asked what is the Celsius temperature of this, so I will subtract 273 from that Kelvin temperature and find that the temperature of the gas at this volume is 191.1 degrees C. Let's now move to the pressure-temperature relationship, and that would be what is known as Gay-Lussac's law. Again, I'm going to do a variation of the temperature, and I will note that it affects the pressure of the system. Quite simply, when you increase the temperature, now let's do it in a fixed volume container, like a hard, rigid wall container. If I heat the gas up so that the volume can't change, now they're going to slam into the walls harder and exert more pressure on those walls. So when the volume is held fixed, not allowed to vary like we did in the balloon, now the rigid walls are going to make this increased pressure due to the more dramatic movement of the molecules. It's just going to exert greater pressure on the walls of the container. Now, the proportionality between pressure and temperature is therefore direct, and this is true only for the Kelvin temperature. When P goes up, when T goes up, and P goes down, when T goes down. Kelvin temperature up, pressure up. Excuse me. There's direct proportionality, meaning if I double the temperature, I will double the pressure that is exerted. If I cut the pressure by 1/8, that would mean the temperature had to be cut by 1/8. Mathematically speaking, the formula that does this effect is P1 over T1 equals P2 over T2. As we did with Boyle's law and Charles's law, we can derive Gay-Lussac's law directly from the ideal gas formula. This time when I design my two experiments, I'm going to allow the temperature and pressure to vary. So I will measure P1 and T1, keep the amount of gas fixed and the volume that it's occupying fixed. So from the ideal gas formula, P1 over T1 equals NR over V. Then I will do a second experiment. P2 and T2 are changes in the pressure and temperature, but I will keep the volume and the amount of gas fixed. So P2 over T2 equals NR over V. Since the amount of gas and volume did not change, the right-hand sides of both these equations are the same. And so therefore the left-hand sides of both these equations are the same, or P1 over T1 equals P2 over T2. Okay, let's look at an example using the Gay-Lussac law. And again, in this case, I will have a varying temperature and pressure. If I was going to use the ideal gas formula, I would have a fixed volume, temperature, and amount of gas. But here I'm varying the temperature and pressure of the gas. So when I measure its initial pressure at 1.25 atmospheres at 12 degrees C, what will the pressure of the gas be at 505 degrees C? So P1 over T1 equals P2 over T2. I rearrange that to P1 T2 equals P2 T1. So if T1 is 285 Kelvin, that's the first temperature with 273 added to it. T2 is 778 Kelvin, that's the second temperature with 273 added to it. I solve for P2 and I get, by all the cancellations of the Kelvin units, I get 3.41 atmospheres. When the temperature goes up, the pressure goes up. Second example of sticking numbers into Gay-Lussac's law. I have a pressure of 815 millimeters of mercury at 26 degrees C. So what is the temperature in degrees C for the pressure to be changed to 725 millimeters of mercury? Again, I start with my Gay-Lussac's law. Again, if I had fixed temperature, pressure, volume, and amount, I'd just go with the ideal gas formula. When I have changing amounts, I use the 1, 2, 1, 2 formulas. I have my temperature changed to Kelvin for my T1. I have my two pressures. I'm going to solve for T2. When I do so, I get 266 Kelvin. The three gas laws that we've seen previously due to Boyle, Charles, or Gay-Lussac can be combined into a single formula. P1 V1 over T1 equals P2 V2 over T2. Notice if you take the pressure out of the combined gas law, it looks like Charles' law, V1 over T1 equals V2 over T2. If you take the temperature out of the combined gas law, it looks like Boyle's law, P1 V1 equals P2 V2. Or if you take the volume out of the combined law, it looks like Gay-Lussac's law, P1 over T1 equals P2 over T2. So this just shows the combination effects of all three. Now again, what we could have done is derive this from the ideal gas formula. I'm not going to do that, but you could easily, because I have an experiment where I allow now all three of these parameters, P1, V1, and T1, to change simultaneously. So I do this for a closed system where N remains fixed. If I take my ideal gas formula and solve it for the correct variables, I would have P1 V1 over T1 equals NR. Then I design a second experiment where pressure, volume, and temperature are changing. So I have P2 V2 over T2, and that should be equal to P2 V2 over T2 equals NR. Since N and R are the same for a closed system, then P1 V1 over T1 should equal P2 V2 over T2. Example using the combined gas law. Now in this particular example, you can't use Boyle's law because we have changes in volume, pressure, but also temperature. You can't use Charles' law because again, you don't have volume and temperature only changing, pressure is as well. You can't use the Gay-Lussac law because not only are pressure and temperature changing, volume is changing as well. So you have to use one where you can allow all three to change simultaneously. P1 V1 over T1 equals P2 V2 over T2. I'm asked to find what is the final volume of the gas when I change the pressure and temperature. So I'm going to solve for V2. First thing I need to be able to do is rearrange the formula to solve for V2. And V2 by rearrangement is T2 P1 V1 divided by T1 P2. So that will be the formula I need to solve. From the above, I will stick values into the formula. Notice, of course, again, just like for Gay-Lussac or for Charles, the temperature must be in Kelvin. So I put my temperatures in Kelvin in the formula, put my atmosphere values in as well as the volume I know. Notice the atmospheres cancel in the numerator and denominator. Temperatures cancel in the numerator and denominator. The answer comes out in volume units as it should. And when all these are plugged in, I get a volume of 4.2 liters.